Okay, very good morning, and I once again welcome you all for the session, second session of the day. I hope my voice is clear and audible. Dr. Rajesh, are you able
Are you
to?
able to?
Yes, I can hear you.
Okay, okay, sir. If you could have any kind of slide, and if you want to check whether it's showing properly, then we could go through it.
Fine. I'll do it. Can I?
Yes, sir. You can share it.
Your entire screen, a window.
A window. If you want to share only the presentation, then I would advise only a window. If you want to toggle between two windows, then entire screen would be preferable.
Okay. One second.
Sir, is there any problem?
Let me try. Okay.
Okay, sir. Okay.
Is it fine?
Sir, I think you need to present it. It's coming on, sir. It's good.
Oh, yeah.
Okay, sir. Sir, just go through the presentation mode.
Okay.
Go
How
for
is that?
Sir, on your bottommost corner,
Okay.
there is just beside the percentage of zoom, you have one cup kind of option on your bottommost right corner, sir.
Okay.
Or you can just press F5.
Okay.
Sir, I think for us, the presentation is visible. So you need to select the window where it is being presenting now, sir. Sir, what I would suggest is stop sharing
Okay.
and then select the window where the slide is being presenting.
Yeah.
Okay, sir, we are waiting for this sharing to begin. Okay, so start the slow, sir. Start the show if you want to change something.
Yes.
Okay, sir. We are not able to see the slideshow. So, sir, can you go through the steps which, as soon as I speak? So I think we can
Okay. Yeah.
solve that problem.
Tell me. Yeah.
Okay, sir. Now stop sharing, sir.
Okay.
Okay, sir. Now go to your presentation and start slideshow.
Okay. Okay. Slideshow from beginning. Okay.
Okay, sir. The slideshow, I think it's been started right now, sir.
Okay.
Isn't it?
Yes.
Okay, sir. Now hold Alt and Tab to toggle between the slideshow and the Google Chrome window.
Okay.
Okay, so now select the sharing option.
Yeah.
Okay.
Okay.
Okay, so in that, I think a window option, select window option.
Yeah.
Okay, in that, as soon as you select window option, there might be three options.
Correct.
Okay, select the PowerPoint slideshow option.
Okay. and share.
Yes, sir.
Is that okay now?
Yes, sir. Now it's okay. So just move on between two slides so that transitions are proper. Okay, sir. It's proper. Okay, sir.
Okay.
Okay. Okay, sir. So we'll stay at this slide.
Okay.
And we'll start this session, sir. Okay. Thank you, sir. Thank you for your.
Thank you. Yeah.
Okay. Okay. So good morning once again for all the participants, and I'm very happy for you to be on time. So it's my great privilege to introduce you to the second session speaker. Dr. Rijesh M. is an associate professor in Department of Manufacturing Engineering at VIT Vellore. He has worked as an assistant professor in Department of Metallurgical and Material Engineering in Amal Jyoti College of Engineering, uh, uh, Kinjarapalli, and as a lecturer at Department of Metallurgical and Material Engineering in NITK Surathkal. He is a member of professional bodies like Indian Institute of Metals, Society for Failure Analysis, and Indian Welding Society. He has obtained his degree of metallurgical engineering, a master's degree, a master of technology in material science and engineering, and PhD in metal forming, all from the Department of Metallurgical and Material Engineering, NITK Surathkal. His main fields of interest are severe plastic deformation, composite materials, and biomaterials. And he has authored many scientific publications in 3D printing and all the above areas as I mentioned, that is severe plastic deformation, composite materials, and biomaterials. Sir, we are very much happy to have you on this session, sir. Over to you.
Thank you. Thank you for that beautiful introduction, Chetan. Yeah. On this onset, I would like to thank Dr. Rajat Degde, Professor and Dean, JNN College of Engineering, Shivamogga, for inviting me for this ATAL FDP series. I'm so happy to be here to actually share some knowledge that I have regarding this nano structuring of magnesium by the process called as plastic deformation. We call it severe plastic deformation. So when we go we will go slowly and we'll understand what the process is all about. Yeah. By the by, I work in Department of Manufacturing Engineering as an associate professor, School of Mechanical Engineering at VIT Vellore at present. Yeah, when we talk about metal forming, we generally talk about plastic deformation. Plastic deformation, the first thing that comes into your mind when you talk about plastic deformation is a permanent change in shape of material. Got it. Plastic deformation is really bad for the end user, but it is actually very, very essential for manufacturing engineer if you wanted to convert one shape into another one. This is primarily what we understand about plastic deformation. But there are something more about plastic deformations. Plastic deformations can actually control the mechanical property of your material. Got it. If you are able to control the deformation temperature and strain rate, you will be able to control the mechanical properties. What I mean to say is, you adopt two different plastic deformation processes to make the same component, you're going to have two different mechanical properties. Just because severity of deformation in one process was slightly higher than the other. So if the customer gives you to make a shape with certain strength, yes, plastic deformation is the one that you have to look for. And how do you achieve that strength that he has told you is something that we'll have to work on. Before we go, we would like to let you know about this this concept of polycrystalline material. The materials that we generally use in day-to-day life for structural applications are all polycrystalline material. What I mean to say is, they're not about single crystals. Got it. This is because when you have a two-phase system, one phase generally nucleates on a high energy sites. If the first figure that you see out here is small nucleus at different locations in the material. Got it. And just after nucleation, the second stage is the growth. Each crystals will add on to the unit cells and they just go on becoming bigger and bigger. We call this the growth process. When every of these crystals grow, you find them not in the same symmetry, just like how you had before. So you will find out an irregular structure where there is an end for a crystal. Got it. I literally say there is an end for one nucleus. Got it. The atoms that is present in this nucleus cannot be bounded with the neighboring one because they are aligned in a different fashion. Got it. That is the reason why these areas are considered as high energy areas. High energy areas where these atoms are dislocated. We call them as grain boundaries. Got it. So if you look at these grain boundaries, they are all high energy sites. They are those sites where the crystals have been broken. They couldn't find a neighbor after that. Got it. So the crystals are broken. That's why grain boundaries are nothing but it's the dislocation. It's a dislocation which has been happened because of this. And these grain boundaries have very high energy because you do not have an atom to pair with. It all started with Hall-Petch relationship, a pioneering work of Hall and Petch. Material scientists and engineers have been attracted by material with small grain size. They say that, finer the grain size, better the mechanical properties. Hall-Petch relationship deals like this: sigma yp is equal to sigma naught plus k square root of d. D is nothing but the diameter of a grain. Got it. A finer grain size increases strength and the fracture toughness of material and provides the potential for superplastic deformation at moderate temperature and high strain rates. So Hall-Petch relationship clearly says that as the grain size reduces, your strength increases. Hall-Petch relationship also tells that as the grain size reduces, your toughness increases. That means that Hall-Petch relationship says that as you control the grains, as you make your grains finer and finer, you are getting a combination of both strength and ductility. Got it. So this was something that is phenomenal, and people have started working on reducing the grain size to a larger extent if you want a better mechanical property. Yeah. Now the orientation difference of one set of crystals to another set of crystals, if you are measuring this difference in orientation, or measuring the degree of misalignment between one set of crystal to another set of crystals, we can always say that if the orientation is not that high or different, your angle will be very low, and we call such orientation as low angle boundaries. Whereas there are some cases where your orientation of one group of nuclei is entirely different from the other. In that case, you get the angle which is really big. We call it as high angle grain boundary. Got it. So the high angle grain boundaries and low angle grain boundaries can be interpreted as the one which is severely deformed or mildly deformed at one point of time. Got it. So see, if you want this high angle grain boundary, or if you want a severe if you go for a severe deformation, you will see this type of misalignments to a larger extent. But if you're going for a conventional forming operations, we hardly get a high angle grain boundary. We get a small misalignment it's called a low angle grain boundary. So this is a schematic diagram of a low angle grain boundary as well as a high angle grain boundaries. This is how a tilt boundary having an angle of misorientation theta results from an element of its dislocations. So these are these are how you get these grain boundaries. And if you look at these grain boundaries, yes, there is a discontinuity at the grain boundaries. It's a line dislocations, and you can see it in the form of a line. Got it. When your grain boundary area is more, you can say that misalignment is more. But plenty of grain boundaries, plenty of misalignment in the material. Yeah. We do have conventional farming operations also. Conventional farming operations like rolling, forging, extrusion, wire drawing, they're all process where they'll reduce a grain size. Got it. Um, there are processes like recrystallizations which happen to the material where the grain size is reduced, and if you do not let them grow, yes, you can get a finer grain size. Got it. So it is not only severe plastic deformation which will give you a finer grains. Got it. A conventional farming operation also will give you finer grains. So Hall pitch relationship works very well for a conventional farming processes also. Got it. Provided you don't let these grains grow. What I mean to say is, if you're if you're going for a conventional farming processes and you hold it for a longer time, by not reducing the temperature of the product, the finer grains may become coarser. But if you do not let them grow, you will get a fine grain structure here also. So a traditional thermomechanical process is nothing but a process where you are using a mechanical process as well as thermal process. For example, you're working a steel at 950 degrees centigrade. We call it as thermomechanical process. You're rolling steel at 1000 degrees centigrade. It's a thermomechanical process where you have temperature of 1000. Along with that, you are applying a mechanical stress for squeezing this material for rolling. So there's a compressive stress and temperature together. We call them by a name called thermomechanical process. And you go for a traditional thermomechanical process, your grain size will be always more than 10 microns. It's so difficult for you to get the grain size less than 10 microns in the thermomechanical process. So in no time, you will have this recrystallization and growth. Because recrystallization temperature is that temperature at which all deformed grains turn out to be new strain-free grains in the span of 1 hour. Got it. And you cannot wait for 1 hour in an industrial process. It happens in seconds by increasing the temperature. You increase the temperature, you can reduce the time. So recrystallization happens in no time. At the same time, growth happens. So controlling it to a grain size less than 10 microns is a tough job in traditional thermomechanical process. Large plastic deformations can in principle be obtained by classical forming techniques like cold rolling and wire drawing. Yes, these are the two processes, like cold rolling and wire drawing, are the process where your deformation is tremendously high. We go for a wire drawing process where we go for 50 meters per second, sometimes 50 to 200 meters per second. The plastic deformation will be that high out here. Many times in a wire drawing process, you'll have to go for a lubrications where the material is not in touch with the die at all. So they follow a continuous strain path and lead to a so-called cellular or fibrous substructure with many low angle grain boundaries. I repeat and underline, low angle grain boundaries. Got it. So you are getting, see, what I mean to say is, even if you are deforming to that extent, the misorientation between one set of nucleus and other set of nucleus is so small, so you get only a low angle grain boundary. We will see what is a severe plastic deformation. How is it different from an ordinary deformation? Got it. It is quite possible for you to get a nano-sized grains or submicron grains in the case of severe plastic deformations, less than 10 microns in most of the times. You have a possibility to change the strain path during deformations, which is not possible in rolling. In a conventional rolling, the strain path is all decided. You have 2 rollers or 4 rollers, which is fixed as per your needs, and the material will only flow in that particular direction. And there is no change in strain path at all. Now, Valley formulated 3 requirements to obtain materials with submicron grain size. So they are, if you want a submicron grain size, you need to have a high angle grain boundary and not a low angle grain boundary. But that is one thing. And the deformation should be uniform throughout the volume of your specimen. That is another requirement. You can always say that large plastic strains may not have generated this internal damage or crack. So when you're actually deforming the material to that extent, there is quite a possibility that you get a shear bands and material cracks down. I don't want that to happen. So in a way, I cannot do a severe plastic deformation on a material which is not ductile. One of the reasons why, if you browse through severe plastic deformation papers, you will find aluminum papers to a larger extent, because aluminum is an FCC structure where the ductility is extremely good. So they can undergo large plastic strain without a cracking. Unfortunately, the material that we are going to talk today is not like this. Got it. They're not ductile like an aluminum. We'll see how we're going to deal with that. So there are many severe plastic deformation processes in the see, these are the conventional ones, and if you look at the past 5 years, people have developed new processes too. So I'll touch upon only the convention. I'll not get time to go through all the SPD processes in this lecture. So I'll concentrate only on the one process out here called as ECAP. So these are the ones which has happened long before. But in the past 5 to 10 years, you can see many new processes which has come. They are equal channel angular pressing, high pressure torsion, accumulative roll bonding, reciprocating extrusion compression, cyclic closed die forging, repetitive corrugation and straightening. They're all popular SPD processes. This is the schematic diagrams. If you look at this, what they're trying to do is, generally what happens in the metal forming process, if you want to roll a material, you take a plate of 8 millimeter thickness, and you bring it down to bring down to 4 millimeter. We have done a 50% reduction. Got it. If you look at the sample, you can see that the dimension of sample has all changed. But in severe plastic deformation, most of the time, what you see in a process like ECAP, we do not change the shape of the component at all. The shape of the component will remain as it is. So in ECAP, you are actually putting an ingot in one channel and taking it out from the other channel, where the diameter of the channels are all same. In accumulated roll bonding, you are going on rolling. When you're rolling, yes, your length increases, your thickness reduces. Then I cut it into 2 pieces and roll again. So I go on rolling like this, till I get a fine grain structure. Repeated corrugations, I bend this, I'll get corrugations. So the next pass I'll do. What I do is I'll repeatedly corrugate this in other locations. By that way, we get the severe plastic deformation. So in today's lecture, I'm concentrating only on a process called as ECAP, called as equal channel angular pressing. If you look at this specimen, this is a big die, and you have made a channel like this inside this die. And you're going to drop your specimen from here, and you're applying a load. Got it. Specimen just cannot come out. So they actually take a turn at these locations. This yellow color shaded region is the where they undergo the tremendous amount of shear. Got it. They shear in these areas and come out. Got it. Now, when you take your specimen out, it will be same as what you have. Very identical to what you have given to them. Got it. But it must have undergone a lot of plastic deformation. It was actually developed by V.M. Siegel in 1977 in the former Soviet Union. It comprises the development of a billet of material through two intersecting channels of equal cross-sectional area lying at an angle 2 phi. And this 2 phi angle can be from 180 to 90 is what we classically define. Got it. They say that, if you have a 180 degree, nothing happens. You drop your specimen, it comes out from the bottom. But there is no load that you need to apply. It just falls by gravity. Got it. So the minimum angle should not be 180. We keep it 150. If it's 150, you will have to have a shear out here. You will have to twist and turn, and then only you can get the product out. Got it. And they say 90 degree has the maximum deformation out here. And there is one paper in ECAP where somebody has done with a 60 degree also, which is on up. So as you see, the angle 2 phi changes from 180 to 90, the severity of deformation goes on increasing. So this is what happens in ECAP. The imposed strain per pass is a function of channel angle. Because the deformation is essentially simple shear in nature, the workpiece undergoes no change in cross-section, this enabling the use of substantially smaller ingots billets to obtain a semi-finished product of a given size. Got it. So there is no cross-sectional reduction that you see in ECAP. The size of the billet is all the same when you take it out. If you look into this example, we find lot of applications when you have. So if you look into the ingot metallurgy, got it. Ingot metallurgy says that whenever you are pouring a molten metal to a cast ingot, you have plenty of segregations. Got it. Because an open pouring that has been taking place, you get a lot of segregations. And if you want to remove the segregation, they say ECAP is a very good way. Got it. Because the deformation is uniform. Got it. Extensive shear is taking place. So if you have some solute atoms segregated in certain regions at higher concentrations, can get into lower concentrations very easily. They just diffuse nicely. All right. So they say that this for ingot metallurgy can be of very good advantage. Other advantage include the ability to impart large strains in multiplus operations and the ability to vary crystallographic textures through judicious selection of processing sequence. Got it. Now they say that, you see, if you vary the way in which you are keeping the billet, got it. See, the first pass, you are keeping the billet in one particular direction. If you are second pass, if you are keeping in the other directions, you can actually vary the slip planes where you can activate the dislocations. Or what we call as activating the dislocation along a slip plane is called as plastic deformation. Got it. So you can actually change the slip planes where plastic deformation can happen, and thus you can change the texture of a material. So that application is something which has been widely used by many researchers. What they do is they change the way each passes are supposed to be, and they see what happens to this material. The ability to impart large strain is especially attractive with regard to obtaining refined microstructures that may provide enhanced superplastic forming. They say that as the grain size reduces, material becomes superplastic. The elongation can go out up to 100,000%. And in that particular case, forming using a superplastic forming method is very easy. So they say that the product that you get from ECAP can be superplastically formed. Got it. So people find, theoretically people find lot of applications to this by looking into this, looking into the process. Got it. One is ingot metallurgy. Second one is crystallographic variation, texture development, superplastic forming, isothermal forging, roll forming. All these things is possible using using an ECAP ingot. Equal channel angular extrusion is another name for equal channel angular pressing. ECAE is a patented one. It's generally not used, but we are so much used to extrusion. That's why. This is a processing technique by which material is subject to intense plastic straining, which produces submicron grain structure without residual porosities. You see that you will not get porosities here. Got it. And the grain size goes to submicron. Less than 10 microns is what I mean. You can get a ultra fine grain. That's one of the reasons why I've took this subject for this magnesium nano materials. This processor will give you a nano structured grains at one point of time, and this nano structured bulk materials has a problem. They do not have ductility. Got it. The Hall-Petch relationship is not valid after certain decrease in grain size. So I should have some mechanisms where I'll have a combination of strength and high ductility by a combination of these grains also. So this high strength and high ductility rarely exist simultaneously. So this combination is very attractive for advanced structural application in areas such as aerospace, automotive, sporting goods, etc. So when you get this combination of ductility as well as strength. The process parameters that we need to concentrate on when you do for ECAE is the diangle, deformation route, number of passes, pressing temperature, pressing speed. We have seen this diangles varies from 180 to 90 is what theoretically we have seen, but 180 degree does not happen. So we can say that it varies from 150 to 90. One paper is there with 60 degree, which has gone an extremely high deformation. Deformation route, how you are twisting and turning your billet after each pass is how deformation route depends upon. The strain path is what I mean by this. How many number of passes will you give? Got it. It is not easy to give a lot of passes, just like how you say. See, what happens is, after each pass, you see a reduction in grain size. The grain size reduces. If you look at the first pass material and the difference in the grain sizes, you can see that there was a tremendous amount of reduction in grain size. If you want to go one more passes, the pressure required to form will be very, very huge, because we ourselves know that as the grain size reduces, the strength increases. So just like how we theoretically say, practically it's not possible to give a huge number of passes. Got it. They say that the ductility of material goes on decreasing as the number of passes increases. Got it. Even though I say it is a combination of strength and ductility, there will be some amount of ductility present, but not to that extent that it can withstand any number of passes that you want. So number of passes are always restricted with respect to the material property. Got it. Like I've told you, another one of the major criteria for a superplastic deformation is they should not crack down. Got it. When you go for this number of passes, the material is not supposed to crack down. That's very important. Pressing temperature is important. Got it. When you are pressing at a room temperature, got it, you are not providing sufficient energy for this grains that is being formed, or the subgrains that is being formed over the boundaries to grow, because you're not giving temperature at all. Got it. Whereas when the temperature increases, you cannot expect fine grains. But sometimes, we have no other way other than increasing the temperature, because material as such is so brittle, you cannot do any cap at room temperature. So we try to increase the temperature a bit, but we may not get an extremely fine grain size, but that's okay. We may get some reduction in grain size if you go and increasing the pressure. There are many other parameters also which you need to look into temperature. Pressing speed is another aspect. Velocity at which you press is another important aspect in mechanics. the equation for strain is something like this. In the case of friction between the die walls and the billets, the strain associated is given by your epsilon n is the strain and n is number of passes. So when this see, I have considered three angles here: 150, 120, and 90, with the internal angle at 0 and 20 degree. And you can see that the least strain is for 150. But very close to 180 degree, you cannot expect a high strain out there. But when you go for 120 and 190, you can see the strain is increased 1.15. So if you're going for 5 passes, your strain goes on adding up. 1.15 plus 1.15 plus 1.15 plus 1.15 plus 1.15. That's how we accumulate strain in the process. So you can give a huge amount of strain provided you can go for a number of cycles. Got it. If you want to go for number of cycles, you need to have some ductility for your material too. So even if you go for 5 passes out here in 150, you may not get a strain which is 2 times as 90. That is also something that you need to understand. So if you find a material which is not that highly ductile to work on, I suggest not to go for a 90 degree. You can go for an angle which is less than that, because material itself is not that ductile to work on. There are 4 deformation routes that we gently adopt in ECAM. One is route A. Route A is defined as that when the billet is extruded without rotation between passes. You are taking billet from the die and putting it back in the same way. You are not doing anything with that. We call it as route A. Billet is extruded without, you're not rotating the billet at all. Whereas in route B subscript A, you are rotating the billet to 90 degree in clockwise direction in the second pass. Got it. When you take it out in the third pass, you are rotating in anti-clockwise directions. Got it. You are rotating 90 degree in clockwise direction in the second pass, and third pass anti-clockwise. And this goes on like that, clockwise and anti-clockwise. We call it as route BA. Route BC is defined as rotation of billet in 90 degree in clockwise direction. So after every passes, you only do a clockwise rotation. And route C is where you go for a 180 degree rotation. 180 degree rotation. It's not same as the one as route A, because route A is basically a 360. It is 180 degree rotation. Yes. Route A, you have no rotation at all. Route BA, 90 degree rotation plus in the first pass, minus in the second pass. It can be the other way also. Whereas in route BC, you are going on rotating plus 90 after each pass. Route C, you're going for 180 degree rotation after each pass. So these are how, so when you do this, what happens is you are allowing certain slip planes to be active. Got it. See, in the first pass, you have activated some slip planes, they have started moving. Got it. When you rotate it, you will not be activating the same slip planes again. You will be activating some other slip planes. So in this case, we expect a dislocation interaction in these cases. Okay. To attain large number of strains, ECA should be repeated multiple times. Accumulated effective one misses strain after n passes. This is strain is equal to n cot phi by root 3. Got it. So the strain, depending upon the strain, you get the number of passes out here. Well, phi is tool angle. During severe plastic deformation, these roots develop characteristic pattern of shear bands after each pass, changing their orientation during subsequent passes. That's what happens. You get a shear band. You get a band of you get a band of dislocations in the first pass. We change the orientations. The slip planes that will get activated also changes. That's all about severe plastic deformation. Now we'll look into the material that we're going to work in today's workshop. That's That's magnesium. Got it. If you look at magnesium, they are friendly material in, if you look in one way, but we have some problems with them too. We look into what are the merits and demerits and how friendly are they. It's the sixth most abundant element in the earth crust. We can say that 2.7% of the earth crust is made up of magnesium. But so we should actually exploit magnesium to a larger extent. And majority of the sources in seawater, the third most abundant dissolved mineral in the seawater. Got it. The attraction is its density. 1/4 of the density of steel and 2/3 that of aluminum. So in today's world, when we are actually talking about specific strength, where the strength to weight ratio is important, magnesium is a very important metal. Yeah, if you look at the atomic properties of crystal structure, I just wanted to point out one thing. I don't want to read all these things. I just want to point out one thing. The crystal structure is not that favorable for me to work on. They got a hexagonal close pack structure. Just because it has got an hexagonal close pack structure, I find it very difficult to work on. If you look from a customer's point of view, he says that a magnesium is a very good material. In spite of being lightweight, they are very hard. That's a problem for me, because my job is to work on the metal, to make it a component. That is not that doesn't become easy for me because of this hexagonal close pack structure. So the problem is about this crystal structure. Actually, strictly speaking, it's not a problem. It's something good for magnesium. Density is 1.738 gram per centimeter cube. Is something that is really attractive. You can actually make components so lightweight with good amount of strength. Melting point is somewhere around 651 degrees Celsius. Yes, that's a good news again. If you allow that the melting point comes down again, and you get good fluidity, and excellent casting can be produced with this. If you look at the mechanical properties, in spite of an FCC structure, we can get an appreciable good amount of strength out here. You just look at this sand cast structures where your ultimate tensile strength is 90 MPa and your yield stress is 21 MPa and your HB hardness is only 30. Right. Things are different when you do a metal forming process. You are getting an ultimate tensile strength in the range of 165 to 205. So a formed magnesium is actually good in the mechanical properties. But the specific strength is high. In spite of these things, the specific strength is high. Now, what you need to understand is the specific strength of this material is high, not because they have got very good strength, just because the density is low. Got it. Sometimes in engineering, we'll have to rework on this, and make sure that the strength is also good to a certain limit. Got it. This is the comparison of densities. If you look into 7.2 gram per cc is what your steel's density is. When you compare to steel, it is only 1.74. Very close to what your plastics density is. And aluminum, which is the most widely used material in aircrafts, may find a replacement soon with magnesium, provided we have good processing methods. Look at the specific strength. Specific strength is nothing but your strength divided by the density. Got it. See, in spite of your casting, strength is not that good, but you divide by the density, just have a look at it. it's coming very close to a rod product of titanium sheet, where it's 190 and here you have 130. Got it. So that's what that's what very important in specific strength. The density plays a major role there. This is one of the reasons why we have this this man, Dr. Kwan Ma, is holding a engine in his hand, which is the most heaviest part in an automobile. Got it. He has cast an engine just 14 kg with a magnesium alloy. Got it. This was once upon a time we used to make this with cast iron, where the vehicle used to be so heavy. He claims that 70% lighter than the cast irons. Got it. Aluminum silicon took over cast iron, which is again a eutectic alloy where the fluidity is good. So many engines now are made up of aluminum, and magnesium engine is 25% lighter than the modern aluminum engine. They say the shock and dent resistance and will dampen noise and vibration significantly more than aluminum is what they claim for this. Not only that, they say that magnesium is a sustainable metal because alloy could save 200 kgs of greenhouse gases over the lifetime of a 3-cylinder car and more in large vehicles. So this is fine when it comes to a casting where you do not apply stress. Got it. Magnesium finds a good amount of application in non-structural materials where stress is not a major criteria. See, you do not put a huge amount of stress on an engine. Got it. That's not the case with the structural material. Got it. We have to structural materials. We have to somehow strengthen magnesium. There are 4 methods that we generally look into. The first 2 methods is not about severe plastic deformation. It's about precipitation strengthening and solid solution strengthening. Both happens to be by alloying. We call this metallurgically strengthening a material. When you alloy a metal, we expect the strength to increase. There are a lot of theories like lattice strains and other things, and thus, yes, they improve the strength just by solution strengthening. Got it. So that's one of the reasons why most of the alloys are stronger than the pure metal. Got it. When I say stronger than the pure metal, I always mean that they're not ductile as the pure metal. Sometimes if you add more than one alloying additions, they may form intermediate precipitates. Got it. And this precipitates can be in nanostructure. You can engineer this precipitates. Got it. You can engineer this precipitate, and you can actually go for a process called as precipitation hardening or age hardening process, where you engineer these precipitates in such a way that they'll block the dislocations when plastic deformation is going on, and then improve the strength. We call this precipitation strengthening. Precipitation strengthening and solid solution strengthening has got something to do with alloying, because alloying elements only will form these precipitates. Got it. So there are 2 different types of strengthening processes, but ultimately due to alloying, they strengthen the materials. And there are 2 types of strengthening that we are interested in here: is grain and sub-grain strengthening and dislocation density strengthening. See, when you are deforming a material in one pass to second pass to third pass and fourth pass, what happens? Your dislocations are moving, your slip planes are moving, and the density of dislocation is increasing. The strengthening of magnesium-rich phase grains is attributed to the impeding of dislocation motion. Ultimately, what happens is when 2 dislocations meet each other, they will find it very difficult for them to move. When they find it very difficult for them to move, dislocation motion does not take place. Dislocation motion does not take place. Plastic deformation does not take place. Plastic deformation does not take place. Strength increases tremendously. So that's what happens here. Got it. The phase grain is attributed to the impeding of dislocation movements formed within the alloys due to prior plastic deformation. Density, increasing dislocation density is by giving prior plastic deformation. Got it. Grain and subgrain strengthening is the strengthening mechanism occurs due to hampering of dislocation movement by the presence of grain and subgrain boundaries. See, this grain boundary itself is a dislocation. So when you are plastically deforming a material, it'll come to the grain boundary. The grain boundary will stop for the plastic deformation. So a finer grain size, plenty of grain boundaries, plenty of regions impeding the dislocation motion. So grain and subgrain strengthening as well as dislocation density strengthening is the one that happens in severe plastic deformation. Now the problem with my material, magnesium, is they are HCP structure. Got it. They have an HCP structure where you have 3 atoms in the center and you have 7 atoms out here, 6 in the corners and one in the right center.
Okay. Excuse me, sir.
Yeah.
Sir, what is difference between the grain boundaries and sub-grain boundaries?
This grain boundaries are the high energy sites where a new phase can be played. For example, a place called a triple point where 3 grains meet.
Okay.
That's a very high energy site where a small grain cannot play. Such grains are called a subgrain.
Okay. Sub-grain boundaries, sir?
Subgrain is formed due to plastic deformation. Clear?
It is clear, sir. Just a small, sorry to interrupt.
Yeah.
Whenever participants are asking questions, so after completion of question, I ask their humble self to mute their microphone, because the speakers, when he's explaining, it would be reverted back to us and there would be an echo coming on it. So you won't be able to properly hear what exactly is the reasoning for your question.
Okay.
Okay, sir.
So if you look at this crystal structure, the problem with this crystal structure is you will not have a plane where this plane get dislocated. If you look at the stacking sequences of an HCP structure, you can see this atoms in the form of A and B, it goes like that. Got it. And there are some planes which are active in this, only few planes, not like an FCC structure where you have plenty of planes. One of the reasons why aluminum is such a wonderful metal, where you have 11 to 12 slip planes, which becomes active when you go for high temperatures. Whereas in HCP, you do not have a slip plane except for this basal slip plane, which needs activation. Got it. So unless and until you activate these planes, it will not get deformed. So a conventional forming of magnesium is very tough, even though there is a light metal. They have got an HCP structure. Not only HCP structure is characterized by C/A ratio. Got it. A unit cell is characterized by the interatomic distance A. The volume of a unit cell is nothing but A cube. Got it. A cube, because they are basically a cube, you know. Whereas you cannot calculate the volume of an HCP like that. An HCP is characterized by C, the height divided by the interatomic distance, C/A. Got it. An ideal C/A ratio is 1.1. The ideal C/A ratio of pure magnesium is 1.624. Got it. But when you have this alloys, you cannot restrict the C/A ratio to 1.64. It can go more than that, and it can go less than that. So that this range is what you have in this. Where you have C/A ratio varies. When a C/A ratio varies, sometimes it is more difficult to deform. because some of the planes do not get activated at all. So that is the problem in titanium. I mean, titanium as well as magnesium. Titanium is a severe problem, and magnesium also have this problem. Titanium C by A ratio is not as good as what you have in magnesium. Got it. So this is the problem what we face when we generally work on titanium, magnesium. Got it. So room temperature deformation. Deformation is nothing but movement of slip planes. Got it. When you have this movement of slip planes, and you do not have a slip plane, where is the deformation taking place? Got it. So if you want to deform magnesium, you have to activate some slip planes. Got it. If slip planes are not activated, slip planes can be activated by increasing the temperature. But when you increase the temperature, the problem is you may not get a very fine nanocrystalline grain. So when you're working on titanium, you need to optimize and compromise on these things. Yeah, this is an AZ31 wrought magnesium alloy, and we see this, we see this this material in a zero pass. You can see the grain boundary is very clear. You can see that can you see the grain boundary is very clear? Some of them are very big, some of them are small, and we call them as equiaxed, even though it is showing some difference. If you take an average, they are basically equiaxed structures. The grain boundaries are very clear, right? Now, when you go for the first pass, you can see that these grains have terribly been disturbed. Got it. And you are getting some subgrains on the boundaries of these grains. This is the answer to the question that somebody has asked me now. You can see the subgrains on these areas, on the grain boundaries. But I don't stop here. I go for second pass, third. See, it's become more terrible. Plenty of dislocation. See, this is nothing but strengthening by dislocation densities. Your dislocation density goes on increasing. Got it. And you go for a third pass again, and you go for a fourth pass. You can get some finer grains. Got it. You can getting finer grains, and these grains didn't grow because the temperature was not that high for it to grow. So that's what happens in ECAP in real. So we are actually this grain refinement by plastic deformation is what we do in ECAP, or in any SPD you do this process, not only in ECAP. This is a 4 ECAP done at 573 Kelvin, because at room temperature it is so difficult to work on magnesium. I would like to see if it was aluminum, I would have done it in room temperature, but in magnesium, no, my slip planes are not active. If you look at this diagram which I show on the left hand side, you can see a lot of parallel lines out here. These parallel lines are nothing but twins. Got it. Twinning is another mechanical working plastic deformation process. When your slip planes are not activated, twinning becomes dominant mechanisms and one of the criteria for twinning will never happen at higher temperature. Why twinning will not happen at higher temperature is because slip planes becomes active at a higher temperature, and plastic deformation takes the least resistant path. It takes the least energy. Got it. Twinning is dominant at room temperature because some slip systems are not active at room temperature. So twinning becomes easier. The force required, the energy required to twin is easier. If you look at magnesium at 573 Kelvin, it is twinned. Got it. It's in the as received conditions. And after 4 passes, you see, still you see some few twin bands, but majority of them have been gone for a fine grain structure. Okay. Yeah. If you look into very closely about the crystals, see this XRD peaks are nothing but the fingerprints. They say that when the diffraction takes place only at certain angle called the Bragg's angle, and you rotate your unit cell in different fashions, your planes with certain density will have certain Bragg's angle and will get diffracted. Got it. So the as received material is basically like this. Got it. These peaks corresponds to the peaks of of magnesium. Got it. This peak corresponds to the peaks of magnesium. Got it. When you homogenize it for a longer time, yes, you get the same peaks because it's the same magnesium again. There will be some peaks which must be shooting up because of stress relieving and other things. But if you look at this material after recap, what must have happened is there must be some planes which is never active have got activated now. See, 101 bar 0 plane, got it. The first plane in the as received condition, got it. You can strongly see that in as received condition. You do not see that in ECAP specimen. Got it. So plane for the received material and homogenized show a strong intensity of position perpendicular to the channel direction. You don't see such tendency of at 573. You don't see this plane at all. And because deformation has taken place. Deformation generally takes place in the basis slip system. 002 and 112 bar 0 of the material is operated after recap. So these two material, this was not operated in the as received condition at all. You can see them getting activated after recap. So intensity of planes were observed to increase after 4 passes. Got it. By contrast, intensity of plane 101 bar 0 decreased significantly in 5 cm. So this is what this XRD peak clearly gives an indication that by doing a civioplastic deformation, you are exciting all the slip planes. Okay. Now, if you look at the influence of the strain path, got it, like an AZ31 magnesium alloy, see the influence of strain path is something like, are you rotating in 90 degrees after that, or is it an A, B, BC, BA or C? What happens? No, the orientation of the grains becomes different. So this is what I mean by influence of strain path. You can see the fine grain bands 4 pass recapped at 200 degree and root C. Root C is 180 degree rotation. Got it. So in this particular case, you see the formation of sub-boundaries, interaction between two dislocation, basal and second order pyramidal slip systems. Got it. So this fine grains that you see, they are on the boundaries of the previous grain that you had. It's called as sub-grains and sub-boundaries. Interaction form dislocation have lower mobility. Got it. Now, when you have dislocation interactions, they will not move. They have already clinched. It appeared that the angle between the bands and the extrusion direction is about 45 degrees. These bands are approximately aligned in the shearing directions. The presence of these bands is a result of dynamic recrystallization in shear bands and two channel intersection planes in ECAP. This is basically twinning. The parallel lines that you see out here is twinning. Twinning plane in a coarse grain which intersect with each other at an angle 60 degree and 101 bar 2 twinning plane in HCP structure. So it's quite possible that you get a combination of twins. So twinning as well as slipping when you undergo plastic deformation, which you rarely see in an FCC metal like aluminum. Got it. So what I mean to say is, whenever you see a twin band, you need to understand that plastic deformation was tough. I have given a huge amount of stress for plastic deformation. So see, look at the twin bands that you see out here. Twinning in the microstructure of recapped specimen 275 degrees centigrade. And root C, this is pass 1 and pass 2. Even after pass 4, you can see these twin bands. So this is at 275, not at room temperature. Got it. So at 275 degrees, also your slip line is not that active in the case of magnesium, is what I want to tell you in AZ31 Mg alloy. So yeah. Now sometimes it may so happen that you will have to anneal the material. Got it. Suppose you are getting a grain size and you have to anneal your material for various applications. We call it isochronal annealing. Suppose if you when you anneal your material, this annealing material is very, very important. Suppose, see, don't you feel that going for a second pass and third pass becomes so tough? Pass 1 has got a lot of twin bands. It's difficult. Pass 2, again, plenty of twin bands is difficult. After pass 4, it may break. So what I do is I relieve the stress a bit by heating to a higher temperature. All right. Now my worry is, if I heat to a higher temperature and relieve the stresses, will my grains grow? With all the difficulties that I've made it as a fine grain, will it grow after some time? And that is what we deal here. It's called as thermal stability. When we cross-check this thermal stability by annealing at different temperatures, this was done on AZ31 magnesium alloy. The value of microhardness does not change for annealing temperature at 150 degrees centigrade. And then it declines. It declines means, yes, it has got some effect. After 150, it has got some effect. It has declined till 500. Microstructural evolution is observed only above temperature about 250 degrees centigrade. You can see microstructure getting coarsened. This is very clear from this. See, look at the microstructure at 250 and look at the microstructure at 500 degrees centigrade. Don't you feel that this fine grains that you've made has become coarsened? So obviously your hardness will come down. Got it. So see till 250, 300 and 350, I don't see much of a difference, but it's happening. Got it. If you go for a hardness, you'll come to know that, hardness must have come down a little bit, but 400, 450 and 500 is too much coarsening. Got it. So there is a microstructural evolution that has been seen about 250. And if you look at the 400 and above, they are very much non-homogeneous. So in this particular case, we call for secondary recrystallization. That is another problem what we have here. Recrystallization happens when you have a stored energy. But when you have a stored energy of coal work and you are providing certain temperatures, all the deformed grains will turn out to be new strain-free grains. Strain-free grains means soft grains. But that is called as a softening mechanism. Secondary recrystallization is a softening mechanisms in the investigated material, the annealing temperature between 450 to 500 degrees centigrade, which we generally do not want in SPDs. Now they say that sometimes we get a combination of strength and ductilities. Got it. Yes. This grain refinement generally give you a strength to ductility balance. This is so if you look into the different material, like ASCAS and ECAP and all, if you're doing a severe plastic deformation, you can always say that you are getting a good balance of strength and ductility. Got it. This is reported in EZ magnesium alloys. Got it. When you go for an especially cap process, you are retaining that strength and ductility. But otherwise, generally people feel that as the grain size reduces, as the grain size the strength increases, ductility comes down. No, for certain amount of strain, we are getting a good combination of strength and ductility. That's very important in structural alloys. The best combination of high hardness, strength and ductility was achieved after ECAP. The resultant of formation of bimodal structure. Got it. If you want the strength and ductility combination, you need to go for a bimodal structure. Bimodal structure is a structure where you have fine grains as well as coarse grains in different locations. So the fine grains will give you strength, and coarse grains will give you a little bit of ductility, and you get a combination of both. And on top of that, when you have this precipitates like magnesium, zinc, and rare earth metals precipitates, they due to the high stress that you're giving for plastic deformation, they'll fragment and redistribute themselves, giving a good amount of strength and ductility. Got it. They'll not become very coarse particles that where you only increase the strength. Nevertheless, the role of probably newly formed intermetallic precipitate observed in the microstructure should be ignored. But there must be some new precipitates that's been formed due to this stress-induced process. We'll have to ignore that for the sake of our study now. This is what we generally see when you go for this interaction with precipitates. You see plenty of precipitates. We call it intermetallic precipitates. Got it. When you go for if you look at this diagram from A to B to C and D, the number of peaks in D is too much. Got it. The A is an as extruded one, where and the B is you done E cap at 160. C E cap at 200 and 240. Got it. It is said that at certain temperatures, some precipitates are thermodynamically stable. At 240, there are many precipitates which are thermodynamically stable, and they just been formed because when you are E capped at 240. Got it. Similarly, in the case of 200 and 160. Got it. So this precipitates just form. When you work on this, and this precipitates will never make your work easier. They will make your material harder and harder. They will not allow you to process that nicely. Through slow scanning within a 2 theta angle of 40 to 42 degrees, several weak diffraction pattern MgZn2 was seen. The researcher has actually done about this precipitates alone. He has worked on all the precipitates. Diffraction peak located in the 2 theta angle near 41 degree decomposed into several peaks belonging to MgZn2 phase and Mg4Zn7 phase. That's what I'm telling you. See, when you have Mg and Zn, they can have various combination of intermetallic precipitates, and they are stable at different temperatures. Processed by 6 passes, the intensity of the diffraction peak of Mg4Zn7 phase and MgZn2 phase increased sharply. Got it. So we really do not know which are the phases that are going to come after each pass and each route and each rotation, which has to be experimentally found out. When the ECAP temperature was 200 or 240, both Mg4Zn7 and MgZn2 phases were revealed in the XRD pattern. And the diffraction intensity rose with increasing numbers of ECAP passes. Something called superplasticity that we need to look into, again, an ECAP. Is the capability of a material to undergo very large plastic deformation. Got it. The advantage of superplasticity is nothing but forming. Got it. When you know that a material can be plastically deformed to 100 to 1000%, that window becomes very, very important for us to form some component. Got it. And how do we get the superplasticity? And do all materials exhibit superplasticity is what we need to know. And superplasticity is high temperature process, happens above 0.5 Tm, where Tm is the melting point in Kelvin. And high temperature superplasticity is not a high energy rate forming process. It's a low strain rate process, where the typically is 10 to the -3 to -4 seconds. So this is basically like, if we are talking about deformation, it's basically like creep, where you have grain boundary sliding. But the sliding cannot occur without a diffusion controlled accumulation mechanism system. Got it. So this type of superplasticity is sometimes called fine structure superplasticity, because the grains are fine, usually less than 10 microns. So the condition for superplasticity should be more than 0.5 Tm, and the grain size should be less than 10 microns. Got it. When magnesium has a grain size which is less than 10 microns, stable above 0.5 Tm centigrade, yes, we can think about exploiting superplasticity in magnesium. So this is basically a literature where we have seen many ECAP specimens and the grain size reductions. Got it. And the M value, which represents the strain rate, it's called a strain rate sensitivity, is the slope of the stress versus strain rate curve. Got it. Any value which is more than 0.3 has got good strain rate sensitivity. Got it. If you have a 0.8 microns, yes, you have got a M value of 0.3, and your percentage elongation goes to 570 percentage. Very good. Got it. Got it. See, if you look at this. 0.7 grain size reductions out here, your M value is 0.5 and your percentage elongation is 650. So if you get such combinations where your grain size, strain rate sensitivity, and elongation is very high, that is the way you have to look for processing magnesium. Got it. Even though it's a slow strain process, yes, this is a window where magnesium can be processed nicely. Whereas if you look at the elongation that magnesium is getting due to the superplasticity, you don't get it like this in room temperature or in most of the working temperatures. So we have to exploit this phenomena to work over magnesium. They say fatigue is something that is fine grain material have less intensely been studied in the static strength properties. In general, it is observed that the high cycle fatigue life of most SPD is enhanced compared to their coarse grain counterparts. In HCF, high cycle fatigue, the elastic component of the strain amplitude is dominant and the fatigue life is dictated by the fracture strength of the material. But in general, the fatigue limit of the material increases with increasing strength, which is in favor of SPD material. They say that SPD materials have better. So if you look at this, three things: ECAP 1 pass, annealed, and ECAP 8 pass at a stress amplitude of 100. You can say that the annealed one has took a longer time to fail compared to the one. So it does not depend only on the grain size. It depends upon the stress amplitude also. Got it. So this is not the same case when you go for a stress amplitude of 80. 80, the annealed sample didn't take a lot of time. Got it. Whereas ECAP 1 pass took a lot of time for failure. So depending upon the stress amplitude, yes, we can say that there are some materials which are easy to fail and the one is difficult. But fatigue is a different a phenomena where you have a repeated cyclings, and when you have a crack nucleation that takes place in a prolonged time. But the advantage, what we point out here in fatigue, is if you look at these fractal graphs. Got it. The A, B, and C. The C is the one which took 1.1 into 10 to the power 4. But still, if you look at this, the surfaces, we can see that the crack, how the crack grows. Got it. So you can get some finer grains out here, and the crack goes in this particular directions. Whereas in the first one, look at the way the crack propagates. So this SCM images clearly says that why. So if you have very fine grain size, you have a lot of grain boundaries. The crack propagation becomes very, very tough. So annealed material where you have, a transgranular fracture is very, very tough in fine grain structures, which is how a brittle failure happens in fatigue. So if you look at this fractograph of ECAP 1 and ECAP 8 at this 100 MPa, if the first one is annealed, ECAP 1 and ECAP 8 passes, you can see that you can see the absence of twin bands out here. You can see a lot of twin bands out here. The absence of twin bands, when you do not have twin bands in this process, it is expected to have a good fatigue life. So the moral of my presentation is increasing the strain level leads to normal distribution of grain size and decreasing the mean grain size, even though the most part of the grain refinement takes place in the initial passes. What I mean to say is, if you're going for 8 passes, you don't expect anything, any exponential things, an exponential reduction in grain size in the eighth pass. The maximum reduction in the grain size happens in the first pass almost all the time. Temperature enhancement also leads to an increase in mean grain size and decrease in process efficiency. Got it. This we know that, but we don't have any other way other than increasing the temperature, because magnesium just cannot be deformed at room temperature. So when you already know this, I should go for some optimization where I go for a bimodal microstructure, which includes coarse grains surrounded by fine grains, which are the resultant of inappropriate orientation of some grains. In some grains, a kind of twinning is also observed, which can be a result of inappropriate orientation, lack of suitable SIP system, and the presence of twinning in the deformation. So this is one of the reasons why they're difficult to deform, but it's not impossible. We can do it. Thank you for your patient hearing.
Thank you, sir. Participants, now any questions regarding the session? You can either unmute yourself, or if you have any kind of network issues, you can always write in the chat box. I will direct it towards the speaker. Okay. So if there are no more questions or no questions, then anyways, we would break for the lunch, and we have one more session to be continued by Dr. Rajesh sir himself. So we'd be meeting here sharply at 2, and thank you, sir. Would be the same link would be shared. You can join on the same link itself.
Okay.
Okay, so there is so we would meet around 2, and take care until then. Thank you.
Fine. Thank you.
Okay.